Hi there and welcome to another part of my videos, and this time we will talk about hypothesis testing. So what happens here is essentially we can take a sample, and with that sample we can essentially test and see if a claim of someone is actually true or most likely not true. Now before we jump into hypothesis testing, let's start with an example of non-statistical hypothesis testing. It's kind of done very similarly to what we do here in statistics in the real life, and that's within the court. If you're in a court, you have a defendant. Someone is sued, for example, for killing a person. So we have here the defendant. Now the thing is, the jury doesn't know what's the reality. Is the defendant innocent or guilty? What they do is looking into evidence, and based on the evidence they will make up their opinion and either decide that the defendant is guilty or innocent. So it's very similar to what we do here in statistics. So essentially we have a hypothesis, and which we call the null hypothesis. Null hypothesis is described with H naught, which would be like in real life translated to the case where the defendant is innocent. As you know, there is the saying that a defendant is always innocent unless proven guilty. And the same thing is here as well. So we assume that the null hypothesis H naught is true unless we have enough statistical evidence to reject it. Now, we have the other thing which is called the alternative hypothesis H1, which is in this case, in the court case, it would be defendant is guilty, and in our statistical example, it would be something else than the H naught. So for example, H naught could be, the Democratic candidate will win the election, and the alternative hypothesis could be, for example, the Democratic candidate will not be the winner of the election, and so on and so forth. So you can have many, many different examples. Now, that's essentially what we will do. So we will talk about H naught and H1. Every time we talk about H naught, it's the null hypothesis, and H1 would be the alternative hypothesis. So in the language of statistics, if we find enough evidence to reject the null hypothesis and support the alternative hypothesis, we reject the null hypothesis in favor of the alternative hypothesis. So it would be the case like if you have enough evidence to believe that the defendant is guilty. Essentially, in our case, if you have enough evidence to believe that the null hypothesis is probably not correct, but the alternative hypothesis is correct. So, for example, in that case, was the alternative hypothesis, we believe that the Democrat candidate does not have enough votes to win the election. If we have enough evidence to support the null hypothesis, this is what we usually say. We say there is not enough evidence to support the alternative hypothesis. What we never say is that we accept the null hypothesis, right? There's just not enough evidence to reject the null hypothesis. That being said, there are essentially two errors that we can make. There is a type 1 and the type 2 error. What are those two types of errors that we can make? So type 1 error is essentially someone is innocent, and by mistake we convict an innocent person, right? So, which is translated in our case in statistics is we have a null hypothesis that was actually true, but we mistakenly reject the null hypothesis. Of course, it can happen, because at the end of the day, it's all about the sample that we are taking. Let's say here is the mean of our population, and population is normally distributed, and we take a sample, and our sample can end up being pretty extreme to the right or pretty extreme to the left, and we can get some very extreme value. Chances are not high, but it is possible. And if the sample that we are taking is far enough away, then we might come to the conclusion that our hypothesis that the mean of the population being this value, which might have been true, is actually wrong. So that would be, in our case, a type 1 error that could happen. So essentially, we reject a true null hypothesis. Right? So the null hypothesis was that the mean of the population is at this value. We take a sample. Usually, our samples will give a value that is very close to the mean, or relatively close to the mean, close enough to the mean to not reject the null hypothesis. But in some extreme cases, in some rare cases, we might have a sample that is kind of far away, or enough far away from that mean that we assumed in the null hypothesis to reject the null hypothesis, even though the null hypothesis was correct. Of course, it can happen. And this is called the type 1 error. Now, we can determine the probability of type 1 error, as we will see later. And that probability, we call it alpha. That's essentially the same alpha that we used in the previous chapters, if you remember. So, the type 2 error is the other way around. It's our null hypothesis is wrong, so let's assume again that our null hypothesis is that this value is the mean of the population. This is our H0, right? But in reality, the mean of the population is this value, right? Whatever that is. I call it X. So we have again a normally distributed sampling distribution. And now if we take a sample, our sample ends up being, let's say, this value. I call it my sample mean. My sample mean is this value, right? Which can happen. In reality, the sample mean is to the left of the mean of the population. But what we think is that my sample mean is to the right of the mean of the population, because the null hypothesis was that here is the mean of the population, and so what we are wrongly believing is that this is our sampling distribution, and we took a sample that is here, which is not that unlikely. Right? If the population mean is here, that our sample gives a value of that is not that unlikely. So we wrongly believe that this is the mean of our population, that our sampling distribution looks like that. While in reality, this is the mean of our population and our sampling distribution looks like that. I know it's a little bit tricky and it's not so easy, it's kind of abstract. You better maybe rewind the video and look again into it. But essentially, this is a basic idea. So we come up with an alternative, with a hypothesis, and then we take a sample, and based on that sample, we kind of try to figure out, is that hypothesis probably correct or not? Now, a few chapters ago, we did another video that was essentially, we had the dean of the department or something like that, that was claiming that graduates of his department will make an income of $800 per week, if I have the numbers correct in my mind, with a standard deviation of 100. And then we had that student who took his own sample. He asked 25 students or so who graduated a year ago, what was the income, the first job that they got offered, what was the income of that job. And based on that sample, we figured out that it's extremely unlikely to get that sample. So I think the numbers was something like this. The dean was claiming that the average income is like $800 per week. And the person asked 25 students, I believe, who graduated a year ago, and his sample mean was like, I don't know, 700 or something like that. But because he had a pretty large sample size, the sampling distribution was something like that. Oops, was something like this. So it was extremely unlikely that given what the dean claims is true, that you ask 25 people and they report an income of, let's say, $700 per week, or whatever was the number. And that's why we could kind of conclude that most probably what the deed is claiming is not exactly correct. So that's essentially kind of the basis for this chapter. That's essentially what we will do in this chapter. It might sound complex, but it's not really. You just need to give it some time. Maybe listen over the videos multiple times and read, into the book, and you will understand it. So this is essentially the basic idea here, where you have a null hypothesis and an alternative hypothesis, and then based on your sample, you decide which one is true, right? So let me draw it one more time. So yeah, we have type 1 error and type 2 error, so we can reject a false null hypothesis. That's type 2 error. The probability for type 2 error is determined by beta. And alpha and beta are inversely related, right? What does that mean? If I want to decrease the probability of doing the alpha error, the type 1 error, right, I have to accept a higher probability for the type 2 error. I have to accept a higher beta, and vice versa. The only way to achieve a lower beta is if I accept a higher alpha. Given you do not increase the sample size. If you raise the sample size, then you could achieve, a lower alpha and lower beta. But given the same sample size, I know I have taken a sample of, 120 people, and I looked into the values. Then that ratio is fixed. They're always inversely related. Now let me do an example to explain to you a little bit more in detail. So essentially, let's say the null hypothesis is that residents of California have an income of $6,000 per month. And the alternative hypothesis is saying, no, we believe that it is less than 6,000. So what we do is now we need to determine, based on the sample that we took, we need to determine a limit. So here is the limit, for example. Now if we take a sample, and our sample is to the right of that limit, we believe that there is not enough evidence to support the alternative hypothesis, so we do not reject the null hypothesis. However, if our sample mean is to the left of that limit, right, then we say, okay, this is enough evidence for us to reject the null hypothesis in favor of the alternative hypothesis. So we believe that income is less than $6,000 per month. Now, depending on where we set that limit, we influence the chances of having a type 1 or type 2 error. So we increase or decrease the values for alpha and beta. Let's assume instead of having this limit, we choose the limit to be here. I want you to stop the video and think about it. Do chances of a type 1 error, so the probability for alpha, does that increase or decrease by shifting it from this point to that point? Pause the video and think about it a little bit. Okay, so let's take a look here. The line being now further to the right, chances are now higher that I have a sample to the left of this line in this area, even though my population mean was there, right? So even though the null hypothesis was correct, chances are now higher by moving the line to the right. Chances are now higher that I take a sample, and based on my sample, I come to the conclusion wrongly that the average income is less than 6,000, right? On the other hand, what happens here, we know from here that if probability of alpha type 1 mistake increases, probability of type 2 error must be decreasing. right? So let's think about it a little bit. Maybe you pause the video and think about why are now chances higher by shifting this limit from the left to the right, that we run into a type 2 error. Okay, so let's assume if income in California is less than $6,000 per month, it's here, let's say by $3,000 per month. That would be our alternative hypothesis, right? Now, shifting the line to the right decreases the probability for the type 2 error, right? So, by shifting the line to the right, it becomes now less likely that if the average income is at $3,000, I wrongly have a sample to the right of that limit, because the limit is now not here anymore but here. And when the sample is on the right side of that limit, I would believe that no, the income is $6,000 per month, right? So essentially, you must think of it this way. We do not know what the reality is. Do we live in a universe where the income of average Californian is $6,000 per month? Or are we in a situation where the average income is only $3,000 per month? Right? Just like the jury that doesn't know in what situation are we. Do we live in a universe where that person who's in front of me, the defendant, is indeed innocent as he claims? Or are we in a situation where he's actually guilty and just, pretends or claims to be innocent? So same situation is here. And so depending on where we set that limit, we are increasing or decreasing the alpha and beta probability, right? So having it more to the right increases the probability for type 1 error, but decreases the probability for type 2 error in this example. Having it more to the left does the opposite. It decreases the probability for the type 1 error, but increases the probability for the type 2 error. Right? So essentially, the basic idea is I have either this sample mean or that sample mean. I don't know which one is true. I have to just put a limit somewhere. If my sample mean is to the left, I believe this one is true. If it's to the right, I believe that one is true. Right? So in the one case, I would say there is enough evidence to reject the null hypothesis in favor of the alternative hypothesis. In the other case, I would say there is not sufficient evidence to reject the null hypothesis.